Hi, Paul. Let's go.
Welcome to iCANX. We're delighted to have an all-star speaker and panel today for you. And I'm Paul Weiss, coming to you from the University of California, Los Angeles, where I'm a nanoscientist on the faculty of chemistry, bioengineering, and materials science. It's my very great pleasure today to host the iCANX lecture. We can go on to the next slide. Yeah. Today we have Professor Joe DeSimone from Stanford University. And as you see, for the rest of April, we have just spectacular speakers, Professors Xiaoyu Zhang, Zhengyi Yu, and Yang Liu. So please join us each of the following Fridays. So today it's my very great pleasure to introduce Professor Joe DeSimone. I'll introduce our panelists after the talk. Professor DeSimone is a good friend, and he's the Sam Gambier Professor of Translational Medicine and Chemical Engineering at Stanford University. He holds appointments in the departments of Radiology and Chemical Engineering, as well as Chemistry and Stanford's Graduate School of Business. His work focuses on developing innovative interdisciplinary solutions to complex problems centered around advanced 3D fabrication methods, as well as entrepreneurship, digital transformation, and manufacturing. Professor DeSimone was awarded the National Medal of Technology and Innovation by President Obama, the ACS Award for Creative Invention, the Lemelson MIT Prize, the NIH Director's Pioneer Award, the Heinz Award for Technology, the Economy, and Employment, the Harvey Prize in Science Technology, and he's one of only a very small number of people who's a member of all three U.S. academies, the National Academies of Science, Engineering, and Medicine. And I want to leave time for Professor DeSimone to give his talk rather than spending the entire hour listing all his other awards. So it's my fantastic pleasure for the second time in a week to be able to introduce Professor Joe DeSimone.
Well, thank you so much, Paul, and good morning to those of us on the East Coast and West Coast of the United States, and good afternoon to those in Europe, and good evening to those in Asia. Let me share my slides here. Can everybody see my slides?
Yes.
All right, actually, let me stop that for 1 second and make sure I'm sharing it properly. Yep. All right, great. Excellent. Well, nice to be here. Thank you for including me. Coming to you from the West Coast and the United States, and my team is located at Stanford University, but this is a collaboration with lots of folks, and I'll point to them at the end of the lecture. And I thought, given the broader context of this this symposium and organization, I decided not only to think about and refer to what we are doing, but I wanted to put it in context of why we're doing what we're doing and what inspired us. I always am interested in people's stories about why they do what they do, and I thought I'd sort of start there. And for some people, there's influences in their lives that make a big difference, and maybe for some folks that are a little bit older than me, were influenced by the race to the moon and President Kennedy, and that inspired a whole generation of people to think about aerospace and aerospace engineering, and just look where we're at today. And just so many exciting things with SpaceX and all the different countries going to the moon and Mars. It just really continues to inspire the world. Maybe some were inspired by Rachel Carson's book, The Silent Spring, which launched the global environmental movement for so many people. And boy, it seems to be one of the most important topics for all of us today, to be focused on that. And maybe for today's generation, they're inspired by Jennifer Doudna and the work in genetic engineering and CRISPR technologies for really transforming medicine and human health and agriculture and so many different disciplines. Lots of inspirations around, and a lot of people get inspiration from different places. For me, it started with a teacher. an amazing teacher I had at Ursinus College. Ursinus is a wonderful liberal arts college outside Philadelphia. I now chair the board of trustees, but I was an undergraduate there. And I had an amazing teacher that introduced me to the field of polymer science in the chemistry department. And I fell in love with the topic. And I also fell in love with the utilitarian aspects of the field. In other words, polymer science is not only has the fundamental science and engineering and physics, chemistry, but it's also used in so many places. And I fell in love with that aspect of sort of almost in a Thomas Jefferson like utilitarian like perspective. So that was set me on my career, and it's great to point to a great teacher that inspires us. And at the same time, back in the 1980s, there was the really taking off in the area of microelectronics. And this is Gordon Moore and Intel, and just the amazing things that are happening in that field, and in particular, the intersection for me of polymer science and the microelectronics industry, and in particular, the role that light plays, patterns of light that are used to make things. And so my career started in this sort of intersection of polymer science and making things with light. And this area, known as photolithography, is driving so much of the world today in manufacturing. And this is a process that uses a light-sensitive polymer, often a formulation, with photoinitiators and that are sensitive to light that can generate acids and other things. The light is often differentiated in a pattern, and that pattern is generated by passing light through what's called a mask or a reticle. It's kind of like a silhouette, and light can pass in certain regions, not in other regions. And it makes a beautiful two-dimensional image with that light, and that light gets focused down from the mask down to even smaller features using optical techniques. And when the light hits the polymer film on the wafer, it induces a chemical change. And a chemical change often is related to a solubility change. And that allows one to develop the image on the wafer. And that image then can be developed and a pattern can emerge. I used words that made it sound like it was a two-dimensional image, an XY image, and for the most part it is. But if you look carefully, there's actually a third dimension. So maybe we'll call it 2.5 instead of three-dimensional. But this pattern becomes really important to making the structures that we want to make in an integrated circuit. And this is the foundation for building some of the most complicated structures that humans have ever fabricated at a really small length scale that looks like a city of streets and buildings. But this is these are the integrated circuits that drive the economy and memory devices and our data warehouses and driving our large language models today and all the AI. It's just an amazing technology that's had its roots over the years. And this was my first PhD paper shortly after I got my PhD, when I already started my first faculty position, designing some of the polymers used to make these patterns. And it's kind of fun to look at the dimensions and how much smaller they are today relative to where they were when I started. So this is the area of microelectronics and photolithography. And just to capture it a little bit more clearly, this is a wafer. This is a video from Zeiss. This is a wafer. You'll see the polymer solution poured onto a wafer that's spinning, making a really uniform thin film. And then you'll see the patterns of light impinge upon that film and inducing chemistry in the film. That chemistry then can be, once it's exposed, can be developed, and then it could be removed using a solvent selected for one area versus the other area. And then you can transfer that pattern into the underlying substrate using etching technologies. People often put down barrier layers, different kinds of spacers, and then they fill up these layers with metal. They often overfill them. because it's hard to control, and then they polish it back using chemical mechanical polishing techniques. And there you have a pattern, a layer of metal. And then this gets repeated over and over again, and there's often like 7 layers of metal building up these structures, and then that wafer gets sawed apart, and we have all the individual chips that make up our memory devices and our integrated circuits. So that's the microelectronics industry in a nutshell. Again, all driven by patterns of light, mostly in 2 dimensions. And so when we think about this length scale of making things, and you think about what the microelectronics industry has done, and you think about something we're all familiar with, like a red blood cell. A red blood cell has a diameter of 8 microns. And so just to put a biological context on this, Moore's law is basically taking us over the last 50 years from single-digit microns or tens of microns down to tens of nanometers, even single-digit nanometers. It's been a remarkable field and driving things down in that direction. But that's using light to make things that are very small without molds. And we really started to reflect more and more about, can we use light to make macroscopic things, bigger things, things that we use every day in our lives, medical devices, consumer products, industrial parts, components of cars, using light instead of molding technologies. And well, if we wanted to do that, well, what are the foundational principles over the last 50 years in the microelectronics industry, and how can we relate the 2 together? Well, in the microelectronics industry, as we just walked through, it's not very thick. It's a very thin structure. There's only typically about 7 layers of metal in the most advanced chips made today. The light is basically making a 2-dimensional pattern. People don't really care so much in the 3rd dimension because they use 2-dimensional thinking to make things layer by layer. And the patterns are all rectilinear. The cross sections are squared off as they make individual patterns. And it's not uncommon, as I showed you, to have 30 steps per layer. Very complicated to make these layers and transfer them into different components or different materials or different sublayers. And it's not uncommon for a wafer in the microelectronics industry to be in process for like 4 months. It's remarkable. If a wafer going through a factory round and round and round, by the time you saw it into the individual chips, it's typically in manufacturing for 4 months. Well, that's a remarkable industry, the microelectronics industry. If we wanted to make everyday things, well, the differences would be these are macroscopic. So instead of just simply 7 layers, something very thin, we're going to need tens of thousands of layers to make a macroscopic object. The patterns can't all be rectilinear. You're going to have organic kinds of patterns, arbitrary patterns. And boy, if you got tens of thousands of layers, you're not going to be able to afford more than 1 step per layer. It's got to be rapid. And you certainly can't afford something like a running shoe or a medical product to take 4 months to make it. It's got to be made in minutes. So this is the challenge of thinking about using light like we did in the microelectronics industry for making everyday things. And I think it's helpful to think about this contextualization of these 2 sectors. I'm going to try to bring them together at the end, but let me just walk you through this first. So we developed a process that really focused on taking 3D printing from a simple prototyping technology into a manufacturing technology. And so that you can think of this as manufacturing science. And we published this paper almost 10 years ago now. And the approach was to use patterns of light. We're going to use it at 385 nanometers. We're going to be projecting it in a movie, basically, a 2-dimensional pattern, but we're going to be changing it quickly. We got to really speed this up because we want to make things in a manufacturing sense. But the key is that the light is going to be passing through a window at the bottom of a reservoir that contains an organic resin that's light sensitive, kind of like a photoresist, but different. But the key is that this window is not only optically transparent, but it's also permeable to oxygen. And so as you lower this platform that's going to be holding the object, it's going to get very close to this window and not touch it, but close, maybe 100 microns, and it will start projecting light. And I'm going to be showing you a video of a process making the object on the left. This object's a pretty complicated air duct for an advanced aircraft. It's going to be made out of very thermally stable resin, and resin that's got a glass transition temperature at 230 degrees Celsius with almost a 4 gigapascal modulus, an amazing material that's going to be crafted from light. You'll see this platform lower into the reservoir. It'll submerge under the liquid, get close to the window, and then you'll see this two-dimensional pattern of light from underneath that represents a cross-section of the object on the left. And these are static images, but we're changing them rapidly using a digital micromirror array device. And we're projecting that up through the window. The first layer bonds to the metal platform that was lowered in, but it doesn't bond to the window because of the oxygen that's coming through the window. Oxygen inhibits the photochemistry that the light is triggering. So there's actually a gap between the part and the window that's submerged under the liquid. And as you pull the object up, it's drawing liquid underneath it to renew the resin at the build interface. And this process, this combination of approaches, allows 3D printing to go from 100, maybe 100 to 1,000 times faster than a traditional layer by layer approach. Now, how do we change images quickly? Well, that's known technology out there. These are digital micromirror devices, DMDs. Texas Instruments is one company that pioneered this. These are millions of little mirrors on a chip that we use LED light, or light from an LED at 385 nanometers that illuminates the entire chip. And then there's little mirrors on the chip that deflect light in different directions that allow it to create patterns. And so we can change a static 2D image rapidly using this device, and so it looks like a movie. So that's critical for what we're doing. And the window that we use is a special material. It's a composite. It's pretty complicated, but the key ingredient is a fluoropolymer known as amorphous Teflon. It's a copolymer of tetrafluoroethylene and a fluorinated dioxyl monomer. This is some material that we worked on extensively in the early 1990s. It's an amorphous form of Teflon that's optically transparent. It's chemically resistant to almost everything. It's very thermally stable, photochemically stable. But the key is it's among the most oxygen permeable materials known. So it's not too different from a contact lens, something that we all are familiar with. It's optically transparent, obviously, and permeable to oxygen. So it's a close cousin to that kind of material. And so this is actually what the process looks like. I'm going to show you an optical coherence tomography data set, basically a cross-section of a part that's building. We're going to put particles in the resin as a contrast agent, and we're going to start impinging it with light. And you'll see the solid form, and it's shown in this mauve color as it gets picked up from the reservoir. And you see this gap. This gap we call the dead zone. It's only about 20 microns thick, but it's enough to allow that as a part gets pulled up, I'll show the video again. As a part gets pulled up, there's a negative pressure right at the center that's maximized in the center, and it draws resin in underneath it. So it's a beautiful image here of the fluid mechanics that's happening here. And at this interface is really the key that allows the 3D printing to go much faster. Normally, with a normal 3D printer, that gap doesn't exist. The layer will bond to the window. And then when that happens, in order to do the next layer, you have to fracture it off the window, pick it up, allow resin to go back in, put it back down and image again. But this allows us to do this in a much more rapid way. The details of this, I don't want to go into too much detail, but there's a series of chemical reactions that are happening that we have to balance. This is a generic concentration axis shown here. This is a distance from the window up into the reservoir, the z-axis. And so light is coming through the window, and the light is most intense as it exits the window. And as the light goes up into the liquid, its intensity is decreasing with distance. Not unlike, a flashlight in the ocean where the light only goes so far and then it absorbs. So the molar absorptivity prevents the light from going too far, but it travels in a Z direction. I'll come back to that. That light is decomposing a photoinitiator, a chemical compound that when it absorbs light will break apart homolytic cleavage and generate a radical pair. And that radical pair is the key to solidifying the resin. Now, the challenge is, as most of us in polymer science know, that if there's oxygen present in the resin, that the oxygen will quench the radicals. And so typically when you do a free radical polymerization, you have to degas your monomer to remove that oxygen. But here we're going to take advantage of that oxygen, and it's going to inhibit the polymerization as a function of distance, because what's going to happen is the photoinitiator is going to decompose. Once you have a radical, it's got one of two fates. If there's oxygen present, it will be quenched by the oxygen. And once the oxygen concentration gets below a certain level, it will kick off the polymerization. And so the oxygen is being consumed by the light, generating the radical pair, but it's being replenished at the interface with the window. And so there's a gradient in oxygen concentration, which basically defines that dead zone, this distance here. And it's this distance here that allows us to do the resin renewal. And we've worked out all these details. It's taken us a while, but I think of this as a software-controlled chemical reaction to grow parts. It's a beautiful intersection of fluid mechanics, reaction chemistry, reaction engineering, mechanical properties coming together, because you need to know the mechanical properties of the part. There's a lot of forces on the part. Think about if the part's elastic and soft, and this part is very close to another solid surface with a liquid between it, and there's something called a Stefan adhesion force. So just think about if you have a drop of liquid between two plates of glass, it's hard to pull them apart, but that's basically what we're doing. And if one of those components was elastic, it can deform, and you have to work in all those mechanical aspects. But every aspect of the process can be adjusted using a printer, if you design it properly, where the software can control every step, can control the light, control the mechanical motion, control the oxygen. All these things come together. And we spun out a company to really master this, because it took a big investment to pull this together. And we built a business around this, and the company's called Carbon. This is what the printers look like. And the printers are designed with a subdiscipline of engineering called mechatronics. In fact, the founding vice president of engineering that I hired, Craig Carlson, was the founding VP of engineering at Tesla. He got to Tesla before Elon got there, and I hired Craig, and he basically ended up hiring over 50 Tesla engineers to join us at Carbon. We're just down the street from Tesla, and Craig brought out the Roadster and the Model S, and then we moved on. He moved on from there, and we started the business at Carbon. And so I say that because the Tesla car is basically built with the same subdiscipline in mechatronics, software control, hardware, and we have the same DNA built into these printers. So these are connected products. We can push software over the air every 6 to 8 weeks and do upgrades, over the air software upgrades. And you basically have a network effect. The more people use the printer, the more you learn. You can turn those learnings into new software and push them out again. And as more and more people use the printer globally, the better they get. And the printers are now in over 19 countries around the world. And I thought I'd show you this picture. This is one of our factories outside Shanghai, and one of our customers. This is a factory that does a lot of things for Adidas, the athletic wear company, and running shoes. And this is what that looks like. And it's not only the printing process, but it's all the unit operations needed in manufacturing. Because when you print the part with a liquid resin, it's got excess resin on there, and it's not uncommon you need to get that resin off. And it's best to do that in an environmentally stable way. And one of the best ways is to do a spin cleaning process. And we're able to do that. And I've got some new advances that the company just introduced recently with a little video here. So these are all the things you need to do to put together a factory using chemistry. And that resin I showed you there was a pretty simple resin, but there's need for more complex resins. And up to this point, most people realize that light alone is not a great way to make most polymers. Most light-based processes for making plastics lead to brittle plastics. They're useful for some applications, but not advanced resins that would be elastic or have a glass transition temperature that would be useful for aerospace applications, for example. And so with that challenge, we developed what we call dual cure resins. In other words, we're going to use resins that can be combinations or networks of multiple materials. And let me show you one example of that. And that's an epoxy system. This is a light-based epoxy resin, and it uses orthogonal chemistry. That is chemistry that can operate using light. And so this will be a diacrylate-based system or a monoacrylate system that can be free radically polymerized with a photoinitiator. And that can operate completely independently of epoxy chemistry. This diapoxide and a diamine. So you can mix all these reagents together as a formulation, and they often come in 2 tubes because of the reactive nature of these. And you pour that into the reservoir and you print it at 385 nanometers and you generate an object. But the light curing component might only be 20 volume% of the resin. The other 80% is the epoxy chemistry. And so you make a fairly weak object, mechanically weak object, that is basically a network that contains other monomers that you can then do a solid state polymerization with to mature the properties. So it's a 2-step process using orthogonal chemistry. My colleague here at Stanford, Carolyn Pertozzi, just got the Nobel Prize for doing orthogonal chemistry in a cell. She does chemistry in a cell that doesn't screw up the biochemistry of a cell. Well, this is orthogonal chemistry in the 3D printer. We can use light to set the shape, and then we use polymer science to set the properties. And this works for epoxies, for polyurethanes, polyurea urethanes, for silicones, for cyanate esters. All the major classes of materials can be made using this dual chemistry approach. And now there's over 50 different resins that have a wide range of mechanical properties. So the business is heavily started in oral health. The industry that Invisalign created, their patents expired a number of years ago, and they now have less than 50% market share of their industry, and now we basically power the rest. We introduced the world's first FDA-approved 3D printed dentures. We have over 500,000 people now wearing dentures. And then we started these advanced materials and elastomers to replace foam, opening up energy returning materials, energy dampening materials. And now we're heavily involved in the injection molding marketplace. Rigid plastics with amazing ductility or high impact strength, powering all sorts of industries from the automotive industry, the aerospace industry, to the medical device industry. Very exciting place to play. And what's really driving this, digital world, is a fundamental change in design. The classic product design cycle starts with designing things in your favorite CAD software. And when you go from the bits to atoms and you enter the real world, you go to typically a prototyping technology. That is to make a physical object of what you designed. It's not often the same technology to make something. It's often not even the same materials, but you do that to see if it's properly designed, because you're going to cut a piece of steel, a molding technology, in order to make the object at scale. But making steel is expensive, and it's a big commitment. And once you make it, you don't want to change it, but you do that in order to scale up manufacturing. So this is a classic product development cycle. In the digital world, and watch this slide transition, very, very exciting. We just cut out the 2 middle steps. This disintermediation of the manufacturing process, where people are now designing products on the means of production, dramatically enhances product innovation. You can be designing something on Monday morning and testing it out Monday afternoon. It's remarkable. So, the speed of the printer is essential, but this is where the speed of innovation happens. This is where it unlocks people's ideas and moving products forward. And it really is disruptive in the manufacturing setting. So that's the key that's driving everything now. And what we try to do is bring processes together to help people make what they need to make. And I've got a little video to show you here on that.
We salute all those who believe good enough is never good or enough. Those who pursue excellence for themselves and for our planet. At Carbon, we apply our craft using science and technology to push limits and realize products unmatched in performance. Our difference is one you feel, and it is light years ahead of anything else out there. You feel it in running shoes that control energy with every stride. Saddles that enhance your performance and comfort mile after mile. Helmets that increase your protection every time you take the field. Clear aligners and dentures that improve oral health and give you more than a few reasons to smile. Crafted by Carbon is a promise. It stands for dedication and focus to crafting what you and our planet truly need. Ongoing creation of amazing answers to our toughest questions. We salute the leaders, dreamers, and doers who keep creation in motion, who boldly imagine a brighter future and craft it every day.
So this now opens up manufacturing with light that goes well beyond the microelectronics industry and integrated circuits, connectors, industrial parts, consumer parts, healthcare, and dental space, as I shared with you. So pretty exciting space to be. But let me bring you back to this story. Everything I just showed you was made with a printer with a resolution of 75 microns. A human hair has a diameter of 100 microns. Moore's law was basically 1 micron down to tens of nanometers. But the technologies of the microelectronics industry actually are challenged to get up to 100 microns or 1,000 microns because of the elaborate nature of etching processes and the like. And the traditional process that I just showed you only typically goes down to about 100 microns. And so there's a gap here between 1 and 100 microns, or maybe 1 and 1,000 microns, that I decided after leaving the leadership of the company Carbon and restarting my academic lab was to really focus on this gap between 1 and 1,000 microns, because there was a lot of things happening, mostly in academia, where people are making things in this space, but they're often using tools that don't scale, and tools that are often using that can make prototypes and test beds, but are not scalable. And to say something very simple that I think is significant, we don't buy stuff you can't make. And so I decided to focus our lab in the manufacturing sciences world in this gap between 1 and 1,000 microns. And so let me walk you through what the challenges were. First, we have to think about challenges in XY versus Z. Now, the microelectronics industry typically is XY resolution mostly. And so that was a pretty straightforward thing for us to do. Just make smaller pixels. We can do that using optical techniques and software techniques and increase the resolution of our printers. And when we do that, we can print objects that that can be scaled down. And so we just published this paper not too long ago, and this is what the Eiffel Tower looks like printed on the Carbon printer, 75 micron resolution. This is what the Eiffel Tower looks like using the same physics and chemistry I just showed you at 30 micron resolution. And now we see that little guy right there. And that's made with a printer with 1.5 micron resolution that my students at Stanford built. And so this is a pretty exciting development that allows us to use the same continuous liquid interface production technique, the clip process, at high resolution. But if you look carefully, it's pretty good in XY, but it's not great in Z. And I'll come back to that in a moment. But first of all, just think about XY. When we're making small things, we need to scale them up. and it doesn't take very long to print these. And so what we decided to do was to put a roll-to-roll process together, interfacing with the 3D printer. And basically, we're going to print the objects using the classic process I showed you, but instead of printing on a platform, we're going to print on a web. It comes through the printer and adhered onto the platform. That once we print, we can then, because it just takes a few minutes, we can advance the film and just allow this to be done over and over again. We can run it through specially designed rollers so the parts don't get crushed. We can go through different unit operations of washing and post-processing. And this allows us to scale things up. And so this is a printer operating in my Stanford lab. It's printing on the right. You'll see the film advance. And then we go through these different steps. And this allows us to really scale things up and move things forward. And so with that, we're making particles, digital dust, if you will, particles of controlled geometry. These are some simple shapes. You could mold shapes like this using imprint lithography. But then you can start making more complicated shapes, arguably getting into shapes that are hard to mold or might be impossible to mold based on their symmetry designs, and really complicated structures that arguably are impossible to mold. But that's the beautiful thing about light. Light can craft things that are unmoldable using these processes. And these are some of our particles that, working with Heinrich Jaeger at the University of Chicago, these are our particles suspended in a node of a sound wave. And we can watch the physics of these particles, which are beautiful to see the interactions of these shapes coming together and look at their aerosol properties and the like. I love this particular video here. I could watch this for hours on end, these little tetrahedron coming together, doing these little dances. And we look at particle jamming transitions and the like, and as they interact based on size exclusion and shape specificity. And we work on the details of these particles, and we work on scaling them up using these processes. So we're excited about where these can go and opportunities in material science and biotechnology. And it's a beautiful sort of demonstration. But resolution is not just an XY game, it's also a Z game and a Z-axis. But hold that thought. We recently developed a process that's a cousin to what we started with. Remember I showed you that the chemistry and physics of the clip process, as you pick a part up, you generate a negative pressure in the bottom of the part, and it draws resin in from the periphery. And so this is showing you the resin flow from the periphery to the center of this conical shape here. Well, we recently introduced a process that, instead of just using and relying on suction forces, we decided to design a very similar part, but now we have a microfluidic channel in the part that's part of the CAD file, and we fluidically connect it to a port in the platform that we can now mechanically inject resin into this gap. So using mechanical forces instead of suction forces. Now, mechanical forces can be really high. In fact, this can, instead of the object here kind of sticking to the window and you're trying to lift it up like two plates of glass with a drop of water between them, now we're injecting resin into that gap, and it's kind of like a rocket engine. You can actually push it off the surface if you're not careful. And so you have to control forces here even more carefully. But what's happening is now you're mechanically pushing the resin into this gap, and the fluid mechanics is completely reversed. We're pushing resin in and it's flowing out, and we can vary how much we push in and how much we want to draw from the periphery. We have total control of both sources of resin. But what we found is that we can now make the 3D printing process go another factor of 10 faster. We can actually have different resins coming in from different ports and do multi-material printing. We've published on that recently. And this gets us into high viscosity resins that would be arguably hard to bring in from this gap that's maybe only 20 microns thick. And so the chemistry here historically has been a mass transfer limited process. And as we start bringing more and more resin into these, we start now moving closer to a reaction rate limited process, which really speeds up the 3D printing, because the photochemistry can go really fast. So we published on this. We're excited about this. I'm not going to dive too much into this, but we learned something we didn't expect. One of the interesting things was that if we actually tried to make a part with channels in it, and we used a traditional 3D printing process, the traditional clip process, those channels would be closed up. They would be over-cured because light from subsequent layers would cure the resin that's in those holes. But when we were pushing resin through the part, we could keep the holes or the channels open. And we realized that, well, the resin that's being pushed in also has oxygen in it. And so what's interesting to think about is, back to resolution, when you bring light through a silhouette or a mask, it's contained in the XY direction, but light is tenacious in the Z direction. It goes where it wants to go based on the molar absorptivity of the medium. But when your layers are thick, that's okay. And that's what we do at 75 micron resolution with 50 micron thick layers, for example. But when your layers are only a micron thick, the light will go way further than you want. And that leads to overcuring of resin and subsequent previously made layers that might be uncured, that had a negative space that you didn't want it to keep negative, but you now had the light crossing over to it, curing it without wanting to do it. So we have a paper pending now. My student Ian Coates has shown that, if you got channels, if your channels are vertical, there's no worrying about stray light curing it because the light's just going straight up. And you can make a vertical channel with this traditional process and the injection process. But once you have channels deflecting at an angle, as you start making the follow-on layers, this channel's got resin in it, and the light can stray beyond the layer and cure it. And you can see that the channels become cured, and there's no channels anymore. But as you flow resin through, even at 90 degrees, we can keep the channels open. And so now this opens up free-form microfluidics. Really amazing space to play now. Most 3D printers have not been amenable to microfluidics. Typically, microfluidics are made using the tools of the microelectronics industry, layer by layer. But now we have free-form structures, and we're having a lot of fun now making amazing things in this space. And one of the places that I want to focus on here is we're using this technology to make microneedles and microneedle arrays, especially for delivering vaccines. And most of us around the planet are now vaccinated from COVID. And those, if you got a Moderna or a Pfizer vaccine, it was an intramuscular injection deep into the muscle. But the target cells for that vaccine were the migratory immune cells. And we humans have 100 to 1,000 times more migratory immune cells in the dermis of our skin than we do in our muscle. And we miss the majority of the cells when we use an injection into the muscle. There's a lot of interest in using microneedles to deliver vaccines into this space, but this has been known for a while, but it's not emerged to be a reliable and repeatable dosage form. And I would argue that the designs that have been used in the past are part of the challenge. So let's look at microneedle history. Microneedles were established in the 1970s. They were made using the tools of the microelectronics industry to etch silicon, making a uniform array of needles that could be coated and deliver products into the dermis. We call these Gen 1 microneedles. Transformative idea, but very limited materials and designs. Then in the 1990s, George Whitesides and John Rogers and others started developing molding technologies, imprint or soft lithography, imprint lithography. And you can make a master template etched in silicon. You make a mold of that, and now you can make replicas of that. The designs were still the same as you etched in silicon, but you opened up the material space. Amazing new kinds of materials that you could use to make your microneedles from. The sharpness wasn't quite as sharp as they were using the etching technologies of the microelectronics industry and Gen 1 techniques, but they weren't too bad. You lose some fidelity on molding. We call these Gen 2 microneedles. But now, with scale up in 3D printing, we call these Gen 3 microneedles. And now we've got geometries that are impossible to make using the tools of the microelectronics industry. And this brings a lot of value in the delivery processes, the pharmacokinetics, which influences the pharmacodynamics of the vaccines. But now we can also make these microneedles with the injection clip, and they can be powered by microfluidics. And we call these Gen 4 microneedles. So let me show you a little bit about microneedles made using Gen 3 and Gen 4 techniques. Our first foray into this was using our modestly high-resolution printer, 30 micron resolution. We made simple designs. We coated these 3D printed microneedles with vaccines. We delivered them into the dermis And what we found in this paper we published, we found a 50-fold increase in antigen-specific antibodies simply because we're doing precision delivery of the vaccine to where the locus of the highest population of the migratory immune cells was. So, transformative, but we sort of knew what this result was going to be. But now, with our high-resolution printer, we're making needles we couldn't have even dreamt about in the past. And these are lattice microneedles with much higher surface area per needle, with new kinds of functionality. We can coat the needles with solutions that dry and leave a coating on the needles. But very excitingly, we can trap droplets of liquid through controlled interfacial tension in each needle. And we can deliver the liquid, mechanically protect the liquid in a lattice and deliver that into the dermis. Or, and more excitingly, we could freeze dry that liquid, lyophilize it, and now we can have a solid product that might be mechanically fragile, like a cake of sugar, which is the typical lyophilization media. It doesn't have good mechanical properties, amorphous sugars even, where you trap the product as a dry product. Well, why would you want to do that? Well, maybe that was a lipid nanoparticle vaccine formulation. Lipid nanoparticles in liquids are not stable for long periods of time. Remember during COVID, the cold chain issues. There was more talk about freezers during COVID than I think I've ever seen in my life. The challenge of global supply chains. Well, imagine if that were frozen, lyophilized, and now at room temperature, that lyophilized cake is now stable for many months at room temperature. Dramatically changes the distribution logistics around the planet. And what's cool about that is you can take these solid formulations, immerse them into an aqueous environment like your skin, and have your own interstitial fluid, the fluid in our bodies, reconstitute the vaccine in situ. So it really opens up global access in the vaccine space. And so this is what we're doing. And the lab is sponsored by the Bill and Melinda Gates Foundation, and we're now developing vaccines in this space, and we're excited to have their financial support. We can now combine these needle designs with microfluidics, and this opens up even larger volumes of liquids. And so this is some of our microneedle arrays with a fluid backing. And you can see we can deliver liquids, or we can deliver even multiple liquids. So you think about some new drug formulations like the new GLP-1 inhibitors and maybe a myostatin that can be combined with these systems. Or maybe you can have a solid product that is then you just have a saline solution that can dissolve it out of these microneedle array patches and deliver a solid product instantly. So you can have slow release patches, you can have instant release patches, you can do large volumes of liquids. It really opens up a wide range of dosage forms going forward. And we've now been able to show that we can deliver messenger RNA into the dermis and use some of these reporter genes, opening up all sorts of opportunities in vaccines. And that's a real exciting space to play. So that's delivering vaccines into the dermis. Into the interstitial fluid region in the dermis. And interstitial fluid liquids are interesting, very interesting. Humans have 3 times as much interstitial fluid in our bodies than we do blood. Anne, who's on the panel here, and many other people are mining this interstitial fluid. Just think about the transformative nature of continuous glucose monitoring, CGM. It's really transforming diabetes globally, and it's really just the beginning. There's a lot of people targeting many different kinds of molecules in metabolic processes, but even well beyond metabolic processes. And so understanding molecular information at scale is really exciting. And interstitial fluid is a great way to think about that. And there's a lot of interest in these wearable sensors and sampling of this fluid. And I often like to say at this point that there's a company in Silicon Valley known as Theranos. It was a debacle of a company for sure, but maybe they had it right in a way, except for the fraud and they went after the wrong circulation system. They went after blood. ISF, I think, is a place to play, and I think the opportunity for single time point and multi time point and continuous monitoring is a really exciting space. And And we're eager to explore that, and many others are. And just to give you a glimpse, the interstitial fluid is rich in biomolecules. It's rich in immunoglobulins, proteins. There's actually more exosomes in interstitial fluid than there is in serum. And so people are looking at which molecules are found in both serum and in interstitial fluid, and which ones might be unique. And it's just a rich place to play, and we're very excited, and many people, including Ann and others, are in this space. So this is an area we're excited to look at. But what's interesting is when you take a typical microneedle, and if it looks like a syringe needle, just smaller. So think about a needle with a hole in the tip and just make it smaller and smaller and smaller. A microneedle, that geometry, when you push it into the skin, it gets clogged often. The skin, these things are so delicate when they have a hole in them that they can clog. And one of my undergraduates at Stanford was thinking about this, and she said that, well, that doesn't happen to a mosquito. When a mosquito bites a human and inserts their microneedle into, doesn't bite, it inserts a microneedle into the skin, or a bee. And well, why is that? Well, if you look at the designs that Mother Nature has for microneedles, the hole is off to the side. It's mechanically protected upon insertion. Well, we can make that with light, and that's what we typically do. And when you do that, you can prevent the needles from clogging, and it really opens up this area of sampling interstitial fluid. And so we've got all sorts of designs and new concepts coming out where we're really setting records on ISF collection within minutes. Getting tens of microliters collected, and we're excited about playing in a space really to transform molecular monitoring going forward, all enabled by new structures made with light that would be arguably hard to make otherwise. Last topic I'll hit you, and then we'll open it up to the panel. There is a lot happening in advanced materials. And in particular, think about materials like conductive carbon materials or ceramic materials, silicon carbide. This opens up so many different industries, from energy storage to the chemical process industry. The chemical process industry is an industry in the United States that apparently 30% of the CO2 that's emitted to the atmosphere in the US is emitted by burning fossil fuels that drive endothermic reactions in the chemical industry. And there's a lot of interest in moving away from fossil fuel heating to electrically heating. And the most energy efficient way to electrically heat is inductive heating. And so designing new kinds of heating systems integrated with fluid flow is a huge opportunity. A lot of these susceptors in inductive heating are made out of silicon carbide. And so my group, along with people like Jonathan Fan and others here at Stanford, we're now using advanced 3D printing concepts, the high resolution ones I just showed you, with new kinds of materials that are precursors to ceramics and elemental carbon. And what we basically do is we 3D print these advanced resins, and then we pyrolyze them at hundreds and thousands of degrees that convert them to carbon and ceramics. And it's a real exciting space that's opening up all sorts of advanced technologies that are really going to drive the future of where we're going to play and try to tackle some of the world's most challenging problems in these areas. So with that, let me end. I am really fortunate to have an amazing group of students. At a place like Stanford, I've got students from different engineering departments: chemical engineering, material science and engineering, mechanical engineering, computer science. I got chemists, a really great group of grad students and postdocs, and a great team of staff that we have that really drive the whole enterprise forward. And we're really fortunate to have the financial support. Vision without resources is a hallucination, and we're really fortunate to have funding from the National Institutes of Health, Welcome Leap, the Bill and Melinda Gates Foundation, and lots of support internal at Stanford. This is our team. We like to get together. It's a really great group of people. That's Alcatraz in the background. It's probably appropriate for my group to have a photo in front of Alcatraz if you knew this group. And a great group of colleagues in chemical engineering and chemistry, both at Stanford and outside Stanford. And I showed some of their work. Eric Shockvey's been a partner in crime with us in so many different areas. Tom So and Sharon Patiri on the interstitial fluid space. Jonathan Fan, as I mentioned, some of the new things we're doing. Jennifer Liu introduced us to some of the pyrolysis field, Matt Becker in medical devices. So a really group of colleagues, Heinrich Jaeger at Chicago. A lot of these things happen as teams, and we're fortunate to have some of the world's best people collaborating with us. And this is our team at Carbon up in Redwood City. It was an amazing run for me leading that company and really pioneering the manufacturing process. And let me just end by pointing out that some of the values from our lab, you can go on our website and pull this up, and we really want people around the world to recognize that that we can be a destination for excellence from wherever it comes from, and these are important things for us, and we encourage that openness going forward. So with that, let me end. I'm a big fan of making things with light. I love this aesthetic of this video, showing the light actually crafting things. And whether it's from microelectronics to 3 dimensions, it's really an amazing field to play in. I'm fortunate to work with a lot of great people in this space. So with that, let me stop and be happy to move into the panel session here. Thank you.
Thank you so much. Another fantastic talk. I learn something more each time I hear about your work, and look forward, hopefully, to collaborating. Thank you so much. Let me now introduce our panel. Our first panelist is Professor Ann Andrews, a returning iCANX speaker from our inaugural year and a plenary speaker at our upcoming iCANX Summit in Davos. Professor Andrews is professor of psychiatry and biobehavioral sciences and chemistry and biochemistry here at UCLA, where she's also a member of the Semel Institute for Neuroscience and Human Behavior, the Hato Center for Neuropharmacology, and the California Nanosystems Institute. Among other awards, she's received an NIH Director's Transformative Research Award and was named an IUPAC Distinguished Woman of Chemistry. She's a fellow of the American College of Neuropsychopharmacology, I love saying that word, and the American Institute for Medical and Biological Engineering, and past president of the International Society for Serotonin Research. Her groundbreaking advances in vivo sensing became the basis for the chemistry behind and leading President Obama's BRAIN initiative, and now wearable technologies for health and wellness. She shared a panel on health and wellness innovations with Professor DeSimone at last week's Challenge Initiative UCLA launch at the Terasaki Innovation Summit. Our next panelist, next slide, please, yes, is Professor Hangbo Sun, who's on the faculty at Tsinghua University, where he studies ultrafast optoelectronics, particularly on laser nanofabrication and ultrafast spectroscopy, after starting his academic career as a professor and Chengjiang scholar at Jilin University. He's a fellow of the IEEE, the Optical Society of America, and the SPIE. And our next distinguished panelist is our own Professor Alice Zhang, who's a professor at Beida. Her creative research in nanotechnology focuses on high-efficiency energy harvesting and self-powered devices and systems. She's been awarded the National Invention Award of Science Technology, the Beijing Education Award twice, the Geneva Invention Gold Medal, and numerous university, local, and national teaching awards, as well as the Medal of May Day. In addition to founding, leading, and hosting the iCANX Talks, Awards, Davos Innovation Summit and Center, she also founded the IEEE NEMS conferences. And our iCANX challenger today is Ms. Hung Han, just down the street, as a PhD candidate in Professor Wei Gao's group in medical engineering at Caltech. She received her MS in electronic science and technology from Nankai University, and is a recipient of the National Scholarship and a Hyatt Fellowship. So welcome all. Let's take the stage. And our first questions, of course, go to our iCANX challenger. Hung.
Thank you so much for the wonderful talk. It's very inspiring. My first question is I come from the medical engineering department, so I'm very curious about the biocompatibility and biodegradability of the 3D printing object. So there is some requirement for to meet this biocompatibility?
Yes.
Thank you.
Yeah, great question, an important question, for sure. And especially as I point to Rachel Carson's book, Silent Spring, and we think about not only biocompatibility, but environmental sustainability, which are often can be closely related. So yes, the materials have to be thoroughly cured and not have residuals and extractables in them. And what's really nice is that there are protocols for maintaining that or establishing that. And that's why we actually started with these dental products, because there's the clarity of the one needs in that industry are well established, and we developed the techniques. And so now there are millions of people that have been using the Invisalign products, which is the 3D printed parts, not necessarily is just used as a master template to make the mold, but that had to clear that process first. That was the first step. And now we have the world's first FDA-approved 3D printed dentures. And a big part of that was the moving into all the protocols, because now the 3D printed part is in the mouth and with mucosal contact. And so we work with amazing companies in this space that are in the denture space and in the dental night guard space. And so we have dental night guard resins, we have denture resins, and they have all passed all the stringent requirements to be medical products. Now, those are extracorporeal, they're in the mouth. And now at the next level is biodegradability. And we now have some new resins. I didn't talk about that here, that are basically polyesters of different types, aliphatic polyesters that can hydrolyze and can lead to oligomers that are benign and biocompatible. So I showed some of my faculty colleagues there at the end, Jack Boyd and Allison Marston. We're designing materials that are degradable, including like a biodegradable stent, materials that can serve a useful function, maybe in a pediatric application, and but that doesn't have to be physically removed, that can dissolve over time. And so we're developing these kinds of advanced materials, but this is an important direction. And you have to design the materials differently, and you have to be very careful about post-processing, and you have a lot of testing to confirm what you do is done properly.
Yes, thank you so much. I'm very excited to hear about so many products and the advancements you made for this field. And my second question is about, for the additive manufacturing, sometimes we need to add some like metal or like iron oxide or some drug. So is it, but for iron oxide, it may be interfere with the light. So do you have some suggestion to solve this problem?
Yeah, so it can often lead to scattering, and so it can be a challenge for some of the resolution issues. But we've had a lot of success. A lot of the resins we have are filled resins. They have particles in them of different sizes. The gap for pushing resin in or pulling resin in from the side, the gap's only about 20 microns. So you have to think about your particle size. You certainly have to think about viscosity. But we've put magnetite into these resins and make parts that have magnetic characteristics. We use pigments all the time. We use phase transfer components that can lead to cooling that allow medical or sportswear that can be cooled through melting transitions. So there's lots of things that people are doing and lots of opportunities for doing that. Drugs are more complicated. We've done that too, but I think I would not try to push something like that through the FDA, but because putting drugs in the resin, the printer, you have to be worried about some chemical changes that would happen with light and other things, and certainly biologics can cross-link, and so you got to be careful. We've done it, but I don't know that we're going to move those into the clinic anytime soon.
Okay, thank you so much.
And we have a question from one of our listeners, Rusen Yang in Xi'an, who asks, well, first says, thank you for the great talk. The amazing 3D printing techniques are surely irreplaceable for customized structures, such as for sophisticated parts that cannot otherwise be achieved. What about structures that can be fabricated with conventional methods? Can it be used competitively for mass production in addition to prototypes?
Yeah, that's a good question. So if you can make something by traditional injection molding, you'll have to think carefully whether you want to make it by 3D printing because it's going to be more expensive. Think about something as simple as forks and spoons. You might as well injection mold those. You don't need to 3D print those. Now, as you get more complicated, think about electrical connectors with deep wells and complexity. And you have to think about, well, how many of those do you need to make? And you think about the supply chain issues. There are billions and billions of dollars worth of parts sitting in warehouses around the world, often in environmentally controlled places that are waiting to be used as spare parts. And that capital is tied up. If you're a CFO today and the number one thing you want to do is free up capital. And everyone at Stanford, and I've got financial people at Stanford always trying to think about freeing up capital. And but if you've got it tied up in inventory, that's a problem. Imagine a warehouse in the cloud, on-demand products. And so you think about all the costs associated with that. And there's some great opportunities for changing business models. But clearly, the best opportunity is making things that are unmakeable or bespoke. And there are electrical connectors that some of our customers are now making that you can't make by injection molding. They're not bespoke. They're making millions of the same thing, but they're a design that can't be made by injection molding. And 90% of the warranty issues in the automotive industry are electrical failures. And 90% of those are caused by electrical connectors that come apart inadvertently. And we've got customers now that have designed electrical connectors that require twice the retraction force for coming apart. And they're way better products and they're unmoldable. So it's not just bespoke, it's designs that are unmakeable that really open up things.
Fantastic. Thank you. Let's move on to Professor Sun.
Okay, I think you have demonstrated very beautiful structures achieved by the three-dimensional printing. I have two questions. The first is, in your case, always you use photopolymer as a structure component, but for enhanced mechanical strength, you should introduce some additives. So do you meet some problems by controlling the percentage of these two composition? For example, for ease of the structure formation, the concentration of the polymer should be high. And if you wish to increase the mechanical strength, for example, you add metal or some other materials, you should increase its percentage. So do you have problems in controlling, in playing this trade-off? So this is my question.
Yeah, so a great question. We're always pushing the limits on performance of the products. I will tell you that, that one resin I showed in the very beginning, that sort of yellowish resin, is a cyanate ester material. It's an amorphous resin. It's got a glass transition temperature of 230 degrees Celsius, and it's got a 4 gigapascal modulus. Pretty impressive already as an amorphous resin. Now to add additives that it can enhance that, or maybe flame retardants or other things, we've demonstrated with the traditional process where we're drawing it in from the sides, we can add a modest amount of additives, but we can't add a whole lot because the resin viscosity gets too high. But with the new injection process where we're mechanically injecting resin, we can go to much higher viscosities now. And so our loading of additives can be much higher, and that opens up a new era of advanced materials using that approach. Now, the other thing I showed it right at the end that I'm really excited about is this convergence of pyrolysis and 3D printing. And now we're thinking about resins that, think about carbon fiber. Carbon fiber used in aerospace. Carbon fiber is made from a polymer of acrylonitrile and you spin a fiber, solvent spin a fiber, and a fiber is a high surface to area, surface to volume material that gets pyrolyzed to advance carbon. Well, most people don't pyrolyze three-dimensional objects because you can't outgas them. But we can pyrolyze a lattice beautifully because it looks like a stitched fiber. And now this opens up advanced materials such as silicon carbide, which is got some of the properties you're alluding to. So there's different ways of tackling this, but there are still challenges, to your point, related to viscosity and percent additives.
Okay. So the second question is, I want to discuss with you about the resolution. So actually, I'm doing the things very similar to you, but I am using femtosecond laser and induce two-photon photopolymerization. In those cases, the vertical resolution is not a big issue. But in your case, even if you use the oxygen as a radical quencher, still you have to control the layer thickness to achieve the third dimension. So do you think your technology is promising for the future circuit printing? For example, certainly for the electronic circuit, the resolution is too high, maybe still far. But for the optical circuit, do you think your technology could be used? Because for photonic circuit, and the size is generally several orders larger than the electronic case. Okay.
Yeah, no, that's a great question. First of all, I'm a big fan of two-photon lithography that you're working on. It's amazing, and it's hard to beat the resolution that those techniques have. Really hard. Those are direct write techniques, and I think they can be challenged by scale up. But it's not, nonetheless, it's got high resolution. So you got this trade-off of resolution and throughput is always there. But we'll face some limits using the approaches. But I grew up in the nano world a little bit, like Paul and others here, and Richard Feynman used to say there's plenty of room at the bottom, right? Thinking about as you make things smaller and smaller, you get plenty of room at the bottom. I like to say there's a lot of room in the middle too, and that's where we're playing, from 1 to 1,000 microns. It's not in the nano world, but there's this gap that we face, and that's sort of the strategy of our thinking was the microelectronics techniques have been awesome, and it's hard to outperform them in the tens of nanometers, and we've been really thinking about where we're going to play and how we're going to win and where the value is, and I think this middle ground is sort of, that was our rationale. But I don't know how far we can push it. I don't know how far you need to push it because there are other techniques that are already out there.
Okay.
Terrific. Thank you. Let's go on to Alice.
Hi. Yeah, great talk. Actually, yeah, we got a lot of attention here. I first must report to, Jill, that we have more than 2,000, 20,000, people online here, very active. Yeah. So, I have a question maybe out of the box. Okay. Jill, I saw you, engaged with commercialize a company or several companies, in your career, and you also were high productive, in the research. So how you handle all these two positions?
We just had an amazing meeting at UCLA that Paul and Ann were at that talk about this. This is important, I think. This intersection of science and impact, commercialization, and it's fraught with challenges. It's fraught with structural, organizational challenges. But I think it's crucial for us to get this right. And let me explain it this way. There's a book out there by Peter Thiel called 0 to 1, and it's about ideas. And in his book, he talks about ideas. A 0 to 1 idea is a breakthrough seminal idea. And then there's 1 to N ideas that build off the seminal idea. And in his book, his supposition is that at the core of a lot of 0 to 1 ideas is an idea that you alone believe in that nobody else does. Okay, put a pin in that for a moment. Now let's go get that idea funded. You know, vision without resources is a hallucination, right? You need money to drive things. Now let's go to in academia, you go to a funding agency like the National Science Foundation or the National Institutes of Health. And it's a consensus peer review process. And it's so competitive today that, you know, you get 6 colleagues that have to give it an excellent review, because if you get 5 excellents and 1 very good, it might not make the pay line, right? What's the probability of an idea that you alone believe in that nobody else does to get 6 excellents? It's really low. Okay, now you go to talk to the venture capitalists. And in Silicon Valley, there is a road called Sand Hill Road, which is right next to Stanford. I thought Sand Hill Road was a metaphor. It's an actual road. And it's where all the venture capitalists are. And you can go to Sand Hill Road and hit 40 different venture capitalists. And you could get 39 no's and 1 yes, and you're in the game. And to me, that's the beauty of venture capital. It's the risk-reward ratio. It's the change the world area. And so I think some of the most innovative people on the planet are in universities. But our funding mechanisms get in the way of innovation. That's ironic. And so we've got to find bridges between the private sector and the academy in order to move ideas forward. And so I'm a big fan of this intersection. I'm a big fan of managing conflicts of interests. And we used to have a chancellor at the University of North Carolina that said he wanted his faculty to create as many conflicts of interest as possible and have a university manage them. What that meant was that a conflict of interest was an engagement with outside the university. And we're for those collaborations. How do you manage that? How do you protect students? How do you protect the sanctity of publications and true science? And I think there's ways you can do that. Now, there's some conflicts you can't manage, dealing with medical devices and people. And there's some institutional conflicts, but I think it's, for the most part, getting this right. It's one of the most important questions you asked, Alice, is getting this right is really important for global innovation. And it's not quite right yet, and it takes attention and intention to make it happen.
Okay, great, Jill. I really like your answers. You know, this was a topic for Davos Summit. Actually, we try to, you know, make the people to talk about this, you know, not only science and technology, also go to the market, the industry, you know, how to get all this engaged together. As you mentioned that it's important, you know, the ideas you believe and you made it, you have to, you know, get influence to the whole world, not just, you know, beat it by, you know, other colleagues or support, you know, yeah, maybe just only one say that's good, you know, that's not excellent, you know, I don't like that too. Okay, let's go talk about this and Davos. I hope, you know, yeah, we can get some solution. Yeah, actually, we got another question, Paul, I sent to you. Yeah, did you
Yes, I
get
see
it?
that one.
Yeah,
This is from
please.
Yi-Quan Lee at HKUST, who asks, is it possible to use your technology to make organic semiconductor devices instead of using conventional semiconductor fabrication processes such as photolithography?
Well, my colleague Zhenin Bao here at Stanford is very much into this space, and we've got some efforts to try to do this. You know, those are beautiful molecules that Zhenin and others do use in that space. You know, we have to have the right optical density, the right photochemistry to make them. I think there's ways of doing this, maybe through filled systems too, but electrically conductive systems are very exciting and you know, would be a great horizon to spend more attention on, and because there's a huge opportunity in that space, and there's a huge need for complexity that's enabled by three-dimensional structures, and it's one that you know, I don't have anything to point to right now, but I think it's a great intersection of where to play.
Very good, thank you. And we're on to Professor Andrews.
Thank you, Joe. I learn something every time I hear you speak. I get additional richness. Joe and I had the pleasure to speak back to back many years ago, and to watch this story continue to develop.
Thank you, Amy.
I was also thinking about what you said about, the idea of 0 to 1, and just musing about how many potentially breakthrough 0 to 1 ideas die on the vine, right? There's so much investment from our governments, both in China and the United States to get us to that, get us to those 0 to 1 ideas, and so little investment after that. So there's just this, another valley of death to think about. I had two questions for you. One is really related to the question that we just had from the audience and to Hong's question, but I wonder, if you maybe can muse a little more outside the box, circling back to your analogies and thoughts and inspirations from the microelectronics industry. I'm thinking about how you might be able to use 3D printing to build, 3D architectures or other types of structures. Of course, I'm thinking about micro needles that may have sensors on them, right? How do we think about moving forward with this beautiful technology you've developed, but being able to now build things that have different materials, or that need different materials integrated into the same device?
Yeah. Well, yeah, I back to your earlier comments, I take a lot of inspiration from your talks and the fields that you work in, and think a lot about your breakthroughs and how we think about complementing them or integrating them is really your question here too, because I thinking about that. I think at the end of the day, I'm a big fan of serial processing too, serial steps. And I think let me sort of give you this example. So the Adidas running shoes, which is a lattice, is designed not only for performance. In fact, the latest design, as you step on the shoe, the lattice design throws you forward 13 degrees.
Wow.
It's amazing structure, and it's amazing for performance. But the lattice is also designed for spin cleaning in the manufacturing step. The shoes are printed on the platform. They go into a centrifuge, and it gets spun at 200 RPM. Excess resin gets flung off, collected at the bottom, goes back into the printer. It used to be washed with a solvent. That's not environmentally sustainable. It's not cost effective. But spinning, collecting solvent, go back in. So this is the digital world. It's designed for performance and manufacturability. And so if you think about that thread and you think about microneedles that might contain a sensor, I think we could design the needles that can have the performance in the application, but also be designed to be subsequently filled with an active ingredient. And so you could think about arrays of microfluidically connected devices. Think about a tray of 100 patches where you can now maybe flow in your sensor in a subsequent, maybe the parts are printed, they're washed, they're sterilized, and then you come in and you backfill with in a GMP manufacturing step, your hydrogel containing a DNA aptamer or some cousin of that. And so I think there are ways of integrating these things. And the fill finish processes, again, in the digital world, open up all sorts of opportunities. And that's how I would start in integrating advanced materials that might be incompatible with a 3D printer, but they can really open up new horizons.
Mm-hmm. So if I understand you, thinking in that serial manufacturing stream, we don't have to make it all at once. We can make one part and then add a part.
Yeah.
And add another part. That's
yeah.
great.
And the cool thing is, imagine if every time you wanted to try a new idea, you had to go remold the object. Mm-hmm. And you had a 3-month delay between every design, or a 6-month delay. But what's cool about this is you can change it every day. Mm-hmm. You can figure this out. That's the digital world. That's a speed of innovation, speed of design that allow you to integrate these multi-step processes.
Yeah, I love that. I love that. So much of my research life has been spent on, doing in vivo studies that take 2 years. So the idea to rapidly, turn ideas over is really exciting to someone like me. I wanted to connect one other thread here, and that again goes back to Hong's question. She asked you about biocompatibility, but you started your talk talking about Rachel Carson's book, The Silent Spring, which was, really it was a really impactful book for me when I first read it. And I wonder if you might comment not just on your ability to recapture, let's say, resin during the manufacturing process, which of course is great for the environment. But have you thought about how you might be able to 3D print polymers that might not just break down, let's say, in the body when they might be used, but let's say you think about shoes, right, being thrown into, landfills. Is there a way to make materials that might break down in our environment and improve, what we're doing there?
Yeah, great question. And to me, here's one of the best examples to think about. This is a dental model.
Mhm.
It's a replica of teeth. It's a replica of teeth when the teeth are crooked. And Invisalign product starts with a 3D printed model, and then you take a sheet of plastic and you melt it on top of this.
Mhm.
And then you laser cut it along the gum line, and you pop off the aligner. And the aligner is the product that goes to the customer. This was just used to make the aligner. This was used for 30 minutes. It's typically thrown in a landfill that's going to be around for 10,000 years. That's dumb. That's just dumb. And that's the problem in society today that we're dealing with. And we have resins that can take this thermoset and turn it back to liquid resin that can be reused again. Problem is, it's probably going to cost 3 times as much. Because it does. You go through that chemical process. It's new chemistries. It's not as simple as this chemistry. There's some costs associated with it. Will society pay for that environmental stewardship as opposed to kicking the can down the road for 10,000 years? Those are the trade-offs that we're dealing with. And this is where policy laws come into play. And this is where companies come into play. And, in the United States, as you know, we've not done a very good job with the recycling industry. The curbside collection process is intrinsically flawed. You could snap the chalk line today in polymer recycling and say, no more research. No more. We're not going to pay for any more research. We have enough ideas out there to implement a dramatic change in what our footprint is on this planet, but nobody wants to do it. Mm-hmm. And so these become the intersection of, that's why it's important. I'm so glad you guys have this forum, but these are where policies can come into play and closed loop product designs. Adidas is an amazing company. Adidas has a new product line they call the Loop shoe. And they believe in a polyurethane economy. Polyurethanes are recyclable, mm-hmm. reversible. Mm-hmm. They believe in shoes that have outsoles, midsoles, uppers, and laces all made from polyurethanes that can go back to original products. And so companies can lead this push as well as nations with laws and policies. But there's costs associated with these things. There's changing habits. And there are things that we can do today without too much changes into science and technology to support them that can be implemented. It's a really important point. Thanks for asking that.
Yeah, yes. And I think you take it in a really important direction, which is that we can't do it alone by just coming up with new ideas in the laboratory.
Yeah.
Well, maybe let me ask a final question, and that's, what would you like to have that you don't yet?
Well, that's a great question. For all our folks there in Asia, I was going to ask which is a prettier campus, PKU or Tsinghua, but I didn't want to start a fight here. But they're both beautiful. Look, I think there are. I would go back to Ann's question. I think I'd love to think about both the policies and procedures and laws that would drive doing things that matter to the world the most, in recyclability, changes in approaches that drive innovation, that can allow more 0 to 1 ideas to come forward. I think those are the things that can really impact the society the most. So I don't want to give a technical answer. I want to give a policy answer. These are the things that I think are most important, and to help unleash the innovation process, help unleash the 0 to 1 ideas, help unleash a more sustainable planet. These are things that we need our organizational leaders. These we need our government leaders to be thinking holistically about what we do. And the world's got a lot of problems, and deep tech is back, right? We've gone through this tech period with software, and the things we're dealing with now are deep tech, and we've got to all work together for a better, safer, more humane planet. And I think science and engineering can play a really important role, and I think we need some partnership at the policy level to help us.
Thank you so much. We've gone a little long because we don't want to let go of you and your wisdom. And I think let's go on to the next slide, which should be a digital certificate, which hopefully we'll hand you in person for giving the 180th iCANX lecture. Probably 360 would have been the perfect number. We were unwilling to wait the 4 years it would have taken to get to that number. So we'll start with 180 and ask you to come back and tell us about your advances when that time comes. Thank you so much for another insightful lecture and discussion, and we're looking forward to seeing you again very, very soon.
Well, thanks for including me. Good
Absolutely.
to see everyone. Thank
Let
you.
me remind everybody about the Davos Summit coming up, which will be a combination of science, technology, innovation, entrepreneurship. There are a number of awards. We've just completed the nomination process, and we'll be going through those very shortly. So have a look at the website to see what's coming. Many of our key speakers will be there in person. And then next week, we'll have Professor Xiaoyu Zhang from UC Berkeley on the iCANX stage. And so we're looking forward to having you back next week and each Friday. And let me thank Alice once again for putting all of these amazing talks together and then putting them up online for us all to share for the future. Thank you all.
Okay, thank you very much. Jill, wonderful talk. Hello, ladies and gentlemen, my dear friends. Welcome to iCANX Davos Summit. So this year we're going to have this big event in Davos, Switzerland. We have 6 topics: innovation, science, technology, investment, management, and entrepreneurship. Short for It's Time. So it's time for us to go together. It's time for us to all these inspiring talks for the future. We'll have Nobel laureate firms. We'll have president of academic firms. We'll have president of university firms. All these big names will be here to talk about the future. What's going on for the future? we also invited all these world leaders, scientists, investment management to go together to talk about, what technology and science going to be for the future. And we're going to listen to many sharp talks. All these great figures was from each field. They will share the sharp ideas, the latest results. So it's not only a platform for all these big names, for these shining stars. We also invite you to share your stories. So it's time for you to deliver a talk here. So you are welcome to submit your materials online. So we have many sub-sessions, parallel sessions. You are welcome to submit your materials, and we're going to pick up someone to share that. And it's our time also invite you to be superstars on the stage. If you are college students, welcome to apply for Innovation Award. If you are young scientists, welcome to apply Young Scientist Award. If you already have your startup, welcome to our Startup Award. All these applications is due April 1st, so you have about months to submit it. And it's time for us to go together. We have all these people here who want to work together with you. So we from different continentals, different countries, different areas. So welcome to join us, and it's our time to go to Davos. Now the pre-registration is open now. You are welcome to submit online and go summit together.
祝你生日快乐！该吹蜡烛了，来，我帮你。啊！祝你生日快乐！生日快乐！
好漂亮的花，我很喜欢。
这是我的礼物，多层陶瓷电容器。
哇，这是多层陶瓷电容器吗？
失败了，没新意。那个我的也是啊。
哇塞，这个不是太阳诱电的多层陶瓷电容器吗？小型、大容量，从原材料开始研发，性能和质量都有保证。我最想要的就是这个了，太阳诱电的多层陶瓷电容器。
你没事吧？
机长，还是你最了解我，有了它让我变得更好。我们是彼此需要的关系。
先生、女士们、亲爱的朋友们，欢迎大家来参加我们的 iCANX 达沃斯科学峰会。那今年是第一次 iCANX 会组织大家一起在瑞士的达沃斯进行线下的聚会。我们有6个主要的议题。第一个是创新 innovation， 第二个是科学 science， 第三个是 technology 我们的技术，第4个是 investment 投资，第5个是 management 管理，第6个是 entrepreneurship 创业。所以它结合起来